All right, guys, I don't have much of a voice today, but I'm going to try to get through 6.1 for you. So chapter 6 is all about undoing what we did in chapter 1, 2, 3, 4, and 5. Okay, this is kind of the other half of calculus. We spent the first half of the year studying derivatives and taking the derivatives of functions. Chapter 6 is going backwards. So we're doing what is called antiderivatives or anti-differentiation, which another name for that is taking an integral. So kind of like division undoes multiplication, an integral undoes differentiation. That's why it's called an antiderivative, is it goes backwards. So one thing that you need to keep in mind when we are taking antiderivatives, when we are doing integrals, you'll see in this example. So the warm-up example wants us to differentiate each of the following. So it wants us to differentiate f of x equals x cubed. So that means f prime of x equals 3x squared. Number 2 is similar, except for it has a minus 10 at the end. But when I take the derivative, f prime of x equals 3x squared, that minus 10 just goes to 0. So number 3, any constant, f of x equals x cubed plus c, is going to end up becoming f prime of x equals 3x squared when I take the derivative. And this is something that we have to be really careful of when we're going backwards, because even though these functions started out very different, we took the derivative and they look like they're the same function. But obviously they're not. There was something that got lost when we took the derivative that we need to be careful of going backwards. So when we go backwards, when we anti-differentiate, we add a constant at the end to make up for that possible constant that disappeared. So this minus 10 disappeared when I took the derivative. This plus c disappeared when I took the derivative. So when I go backwards, I know that the integral of 3x squared is going to be x cubed, but I don't know what number came after that. So we just call it c. That's just a constant. We don't know what it is. Sometimes it gives us information that we can figure out what that number is. But when we go backwards, when we anti-differentiate, we always need to make sure that we put that plus c at the end of our integral. So this problem, you can rewrite it as the integral of 3x squared dx equals x cubed plus c. Okay, now that symbol, I just called it integral. This is called the integral symbol. It looks like a wavy little line. It tells you to integrate whatever comes after it. Kind of like d dx tells you to take the derivative of whatever comes after it. The integral symbol tells you to take the antiderivative of whatever comes after it. We call that the integrand, the expression that comes after the symbol. Now, dx indicates that you're integrating with respect to x, which really won't matter much in high school AP calculus. When you get into college, some of the calculus classes there, you will be working with more than one variable, and it is important to know what you are integrating with respect to. For the most part, we're integrating with respect to just one variable, so it won't matter that much. It doesn't affect the integration process, okay? Now that c that we put at the end, we call that the constant of integration, and it's important that we always remember that one. So a couple of backwards rules. So this is going to look a lot like our lesson where we first learned about derivatives, except for now we're going backwards. We're doing antiderivatives. So the power rule, when we learned the power rule, if I had, let's say, x to the m, when we took the derivative of x to the m, we would multiply this m down in front, and then we would lower it by one number. We would end up with m minus 1. When I do the antiderivative, I go backwards. So when I do the integral of x to the n, I raise the n by 1. That's why this says x to the n plus 1. And instead of multiplying by that exponent, I divide by that exponent because I'm undoing the derivative. I'm doing the opposite. I don't minus 1 and I don't multiply and minus 1. I add 1 and divide. I go backwards. So for example, the integral of x to the 5th power dx would equal, I take the 5 and I add 1 to it, and then I divide by that new exponent. So I could divide by 6, or I could write it as 1 over 6 x to the 6th. Okay, so you go up by 1, divide by the new number. The constant rule, again, we're going backwards. The constant rule for integrating is to add an x to a constant. So the integral of 7 dx is equal to 7x. Okay, you're going, oh, I forgot the plus c on both of these. So you are going backwards. So instead of dropping the x and ending up with a constant, you are adding the x to the constant. The scalar multiple, this is just that same idea that you can take a constant that's out in front and you can move it to the front of the integral sign. So if I had something like take the integral of 7x to the 4th dx, I could rewrite that as 7 integral x to the 4th dx. And then when I integrate, I've got the 7 out in front getting multiplied. So I would have 1/5 x to the 5th plus c getting multiplied by that 7. Okay, so you can move those constants out in front and then multiply them at the end, just like we would when we were taking derivatives. The sum rule works just like the sum rule for derivatives. If you have two different functions, then you can integrate them separately. So if I'm taking the integral of 5x plus x squared dx, I can rewrite that as the integral of 5x plus the integral of, whoops, I need the dx, 5x dx plus the integral of x squared dx. And I can integrate those separately, okay? All right, so let's do some examples. The integral of x cubed dx. So I raise the x's exponent by 1. So it becomes x to the 4th. And then I divide by 4. I like to multiply by 1/4 instead of dividing by 4 if I don't have a number in front. And then I add c. Okay? The integral of 2 is 2x plus c. The integral of t to the 4th plus 2, I can just integrate them separately. So t to the 4th becomes t to the 5th, and I put a 1/5 out in front. And then the 2 just gets a t added to it, and then I get a plus c at the end. Okay? All right, let's do a few more interesting examples that require a little bit of manipulation. Well, I guess 7 doesn't. 7's just got 3 different little functions, and we can integrate them separately. So 2y squared becomes y cubed, and then I need to divide by 3, so that's 2/3. The 4y becomes y squared, and then I divide by 2. 4 divided by 2 is just 2. And then the 1 gets a y added to it, and then I add c at the end. Okay, number 8. You don't know how to do integrals when the exponent's on the bottom and when you have square roots. So we're going to rewrite this to make it look like a power rule, right? Because we know how to integrate the power rule. So let's rewrite these. And the way I do that is I still have my integral. The x squared I'm going to move up and make it x to the -2. The square root x is the same as x to the half. I'm also going to move it up, and I'm going to make it x to the negative 1/2 dx. So the integral of 3x to the negative 2, if I add 1, I get x to the negative 1. And now I have to divide by negative 1, so this becomes negative 3. X to the negative half, if I add 1, becomes x to the positive half. And then I have to divide by positive 1/2. So negative x, or the negative in front, the negative 1 divided by a half just becomes negative 2. And then I need a plus c at the end. So that negative right there came from up above, and then dividing by a half is the same thing as timesing by 2. That's why there's a 2 there. Okay, number 9, the integral of root x plus 1 over x squared. I'm going to split this up first to be root x. Actually, I'm going to write that as x to the half over x squared plus 1 over x squared dx. And then I'm going to rewrite that. I'm going to move the x squared up, and I end up with x to the negative 3/2 when I combine it with the x to the half, plus x to the negative 2 dx. Okay, so when I add 1 to each of these, the integral of x to the negative 3/2, when I add 1, I get x to the negative 1/2. And dividing by negative 1/2 is the same thing as multiplying by negative 2. So I get a negative 2 out front. And then x to the negative 2 becomes x to the negative 1. And then I have to divide by negative 1. So I get a negative out in front of this, and I get a plus c at the back. Now, if you're ever not sure if you did it correctly, just take the derivative. If I wanted to double check my work, then I could say, all right, what's the derivative of this function I just got? Well, negative 1/2 getting multiplied down makes the negative 2 go away. And then I minus 1, so I get negative 3/2. And then negative 1 getting multiplied down becomes a positive, and I minus 1, I get x to the negative 2. And I can see that that's where I started. So if you're not sure if you did it correctly, just take the derivative and double check your work. See if you get back to where you started. Now that you can go both ways, you can check your work as you go. Okay, there's a little note right here. Now that we're adding this c when we take the integral, you just need to remember, don't put a plus c when you take the derivative. Sometimes we start adding c and we're gonna pound it in. You need to remember to add c, add c, add c. But that doesn't mean you always add a c, right? So don't use that when you're doing derivatives, only use that plus c when you're integrating. Now, sometimes they give you an initial condition, so you can actually figure out what that c value was. So example 10 says f prime of x is equal to x to the negative 3. And then it gives me an initial point of my function. And then it wants me to find f of x. Okay, well, f of x is just, if I undo the derivative, which is an integral, then that should get rid of the f prime of x. So the integral of f prime is f of x. The integral of x to the negative 3. So I need to add 1, so I get x to the negative 2. And then I need to divide by negative 2, which is negative 1/2. And then I need to put a plus c. Now, because it gives me this initial condition, now I can plug these values into the function I just got and solve for c to come up with my actual f of x function and get rid of the c value. So f of 1 is 3/2, so that means 3/2 equals negative 1/2 times 1 to the negative 2 plus c. 1 to any power just becomes 1, right? So I've got 3/2 equals negative 1/2 plus c. So if I add a half to both sides, then that means that c is equal to 2. So now I can plug that into my function up here. F of x is equal to negative 1/2 x to the negative 2 plus 2. I can replace that c value with an actual number, all right? Example 11 is tries to throw you off a little bit. Number 11 wants you to take the derivative of an integral. Well, derivatives and integrals just cancel each other out. So the derivative and the integral are going to cancel, and you're just left with 5 root x minus 1 over x squared, right? They just undo the original work. All right, if we know the acceleration equation for an object and are given initial conditions, we can go backwards to figure out the velocity and the position functions in physics. So going forward, position, if I take the derivative, I get velocity. If I take the derivative of velocity, I get acceleration. So going backwards, if I take the integral of acceleration, I get velocity. And if I take the integral of velocity, I get my position function. So example 12 says the acceleration of a particle is a of t equals 4t minus 3. And then it gives me initial conditions for the velocity and the position functions. It wants me to find velocity. Well, velocity is the integral of acceleration. So I just need to take the integral of 4t minus 3 dt. So integral of 4t is t squared, and then I have to divide by 2, so that becomes 2t squared. The integral of negative 3 is negative 3t, and then I get a plus c. So that is equal to my velocity function. I guess I could have said v of t equals the integral of a of t up above, right? Now, I know an initial condition for my velocity. I know that when t is 1, my velocity is 6. So I can use that to figure out my c value. So 6 equals 2 times 1 squared minus 3 times 1 plus c. So 6 equals 2 minus 3 plus c. So 6 equals negative 1 plus c. So c equals 7. So now my velocity function is, I kind of wrote this in the way, didn't I? My velocity function is 2t squared minus 3t plus 7. Now, if I want to integrate my velocity, I end up with position. So s of t equals the integral of v of t. So I need to integrate 2t squared minus 3t plus 7 with respect to t. All right, so s of t is going to equal 2t squared goes t to the cubed, but then I've got to divide by 3, so this becomes 2/3. Negative 3t becomes t squared, and I divide by 2, so I get negative 3/2 t squared. And then plus 7 becomes plus 7t. And then I've got a plus c that I need to add at the end. Now up above, it gave me initial conditions. So I can plug in those values to figure out this c. So when t is 2, my position is 5. So 5 equals, let's see, 2/3 times 2 cubed minus 3/2 times 2 squared plus 7 times 2 plus c. So 5 equals 2 to the third power is 8. So this becomes 16 cubed minus 2 squared is 4. So this becomes negative 12/2. And then this becomes 14, and this becomes c. Yuck. C value is not going to be very nice. If I minus 14 over on the left, I get what? Negative 9 equals, I need to get a common denominator. So 16 thirds, we got to times everything by, yeah, I did that right. 16 thirds, we got to times by 2. So this is 32 sixths. And 12 halves, we're going to times by 3 and get 36 sixths. So 32 over 6 minus 36 over 6, I get negative 9 equals negative 4 over 6 plus C. So if I add 4 sixths to the other side, C equals negative 9 plus 4 over 6. And if you wanted to turn that into all sixes, you could do what? Negative 54 over 6 plus 4 over 6 equals negative 50 over 6. That is not a nice C value. But I can plug that in now to my position function. So S of t equals 2 thirds t cubed minus 3 halves t squared plus 7t minus 50 over 6. And I've got my original function. All right, example 13. Given that on Earth, the acceleration of an object due to gravity is approximately negative 32 feet per second squared. Negative indicates downwards. It wants me to come up with the equation for velocity and the equation for position if I'm given initial velocity and initial position of V naught and S naught. Okay, so if acceleration is equal to negative 32 feet per second squared, I want to integrate these with respect to t so that I can get velocity. So negative 32 becomes negative 32t plus c. Now, if my initial velocity is v naught, all that means is that this c value becomes v naught. That's all that it means by v naught is my initial velocity. Because what it's saying is if I were to plug in 0, then I would get my initial velocity. So v naught would equal negative 32 times 0 plus c, and that just goes away. So then you come to find out that c and v naught are the same thing. So I just replaced it right there. And now I'm going to do the same thing for position. If I take the integral of v of t, then I'm going to get the position function. So if I take the integral of negative 32t plus v naught dt, I get, let's see, t squared, and then I have to divide by 2, so I get negative 16. V naught becomes v naught t, and then I get a plus c. So this is my S of t, but it gave me initial position of S naught. So when t is 0, I get my initial position. So t being 0 makes that go away and that go away, and I'm just left with c. So in this case, c is the same thing as S naught. So my position function is just negative 16t squared plus v naught t plus S naught. And those are functions that you're going to use a lot over the next couple of months. Well, and we already have. We've just used them going forwards, right? We've used them with position and then velocity, then acceleration, but now you can use them going backwards as well, all right? Okay, 6.1 homework. The priority is the new stuff. The old stuff, the review questions are important because it's stuff that you need to remember how to do. But before next class period, put an effort in to get the new questions done at least before you come back to class next time. And come see me if you need any help.